Section 8.7 is titled Numerical Integration. And what we're going to do in this section is we're going to learn how to evaluate definite integrals, not by using the analytical techniques that we've been learning over Chapter 8, but instead by using what we call numerical techniques. And the three techniques that we will address in this section are the midpoint rule, the trapezoid rule, and Simpson's rule. And so essentially what we do here is we approximate the area under a curve. So remember, that's what it means to evaluate a definite integral. It means that you are essentially graphing the curve f of x, and you're looking at its boundary with the x-axis, and you're finding the area underneath that curve. And so we're going to approximate the area under the curve by dividing our given interval from A to B into n equally spaced subintervals. Once we've created these equally spaced subintervals over our entire interval from A to B, what we'll do is we'll divide that area up into either rectangular areas or trapezoidal areas. And then Simpson's rule follows a different pattern altogether. But we'll divide it up into these geometric shapes that we can find the area of individually, and summing them all up will approximate the area underneath that curve, which in essence approximates the value of the definite integral. So let's start with the midpoint. And so it's my hope that each of you has completed that introductory activity that I put up on Canvas, which was the worksheet that had you actually completing a midpoint rule example and then also a trapezoid rule example with my step-by-step instruction. So hopefully you've seen an example of each one of these already. The midpoint, just so you know, is something that we've already done in Calc 1. We'll do it again. Doesn't hurt to do it again. But before we ever introduced any analytical techniques to evaluate integrals, we actually looked at using Riemann sums to show you how to find the area under a curve. So now that we've come full circle and we've learned what a definite integral means, and we've learned a ton of different analytical techniques to evaluate one, we're going to go back to the original technique of the Riemann sum numerical integration, and we're going to look at it one more time. So when we did it in Calc 1, our rectangles were either created from left endpoints or right endpoints or from midpoints. And here we're going to specifically focus on midpoints. So once again, let me give you an idea of what the midpoint rule is doing. So we're taking some function, f of x, and we are looking at it over a specific interval from A to B. And so if I cut this function off at those endpoints A and B, I get this area under the curve, which is what represents this integral that I've written up here. And the idea here is that we're going to take A minus B, and we're going to divide it into n subintervals. Divide it into n subintervals. So remember, in doing that, I create these equally spaced regions, which can be defined in length by delta x. So So the first thing that we're going to do in the midpoint rule is we're going to calculate delta x, which again is the length of each subinterval. And from Calc 1 we learned that delta x can be represented by taking b minus a and dividing it by n. So n should be a given value in the problems that you do, but n can be any number. The larger n is, the more subintervals we have and the more rectangular regions we create, we can actually be more precise in our calculation. So if I only split this up into n equals 2 or 2 subintervals, I'd have 2 different rectangular regions where there'd definitely be a lot of either overestimation or underestimation that would happen based on those rectangles. If I let n become large, and I have several of these, each rectangle will more closely follow the pattern of the curve f of x, and we'll have less error in our calculation. Continuing on, once we've gotten our delta x, we can now determine what the subintervals actually are. So remember that our subintervals, of course, the leftmost endpoint of our first subinterval will start at a, and then we'll have some x1 value. Then we'll have x2 to x3, x3 to x4, x sub n minus 1 all the way up to b. Okay, so we have n number of subintervals. Leftmost endpoint is a, rightmost endpoint is b, and then we have these in between x values that we can determine based on our delta x and what our beginning and ending values are. So the reason that we create those subintervals is so that we can determine which x values within those intervals or subintervals will be the midpoint values. Remember, this is the midpoint rule. So we want to know what's the midpoint of every single subinterval. And in case you've forgotten how to find a midpoint, basically if I use this first subinterval as an example, I would just add up the two components, the lower or first and the left endpoint of my subinterval and my right endpoint. I would add them together and divide by 2, which is essentially just averaging those two values. Alright, so I would need to do that for every single interval. So in the picture that I've drawn, let's say that this is our first interval from a to x sub 1. I'm going to locate the x value that is precisely in the middle of those two. And what I'm going to use that for is to determine the height of my rectangle. So if I went from the left endpoint, I'd have one height. If I went from the right endpoint, I'd have a different height because my curve is not uniform or linear, or constant even, I should say. So the midpoint value is what's going to determine the height of our rectangle. So from here, whoops, I called that step 2, and that should really be step 3. I'm getting off in my numbering here. So that brings me to step 4. I need to find all the rectangle heights, n of them. I'll have n number of rectangles, so each one has a different height, and I do that by calculating f of a, and then f of x sub 1, f of x sub 2, on and on and on, however many I have, all the way up to f of b. Finally, I'm ready to calculate the area of each rectangle. So I'm going to say that I'm calculating and summing all of my rectangle areas. Alright, so I'm going to give you a quick shortcut. It's not much of a shortcut, but it's worth mentioning. Each time I'm finding the area of a rectangle, what I'm going to do is I'm going to take the base of that rectangle and I'm going to multiply it by, of course, the height of that rectangle in order to get me the area of one rectangle. And then I'm going to repeat that again and again and again n number of times. Well, what you'll notice is that the base consistently of every single rectangle is going to be delta x. So what I can actually do is I can factor out that delta x, and I can just add all of the heights of every, whoops, that's a plus sign, sorry, f of a plus f of x sub 1 plus f of x sub 2 plus dot dot dot. So I'm adding all of my heights, and then I can just multiply it by the base, since the base is the same for every single rectangle. And that sum will approximate the area under this curve, which also approximates the definite integral that we're given. Let's move on